Hi everyone, welcome to this OpenRocket tutorial. My name's Brian. I'm doing this in conjunction with Portland State Aerospace Society. After we finish the walkthrough here, if you have any questions, please reach out to me on our Slack server. If you find this video out in the wild, if we end up putting it on YouTube or something, and you aren't a member of PSAS, that's fine. If you have questions, you're welcome to email me at the address on the screen. There's also lots of other great resources out there on YouTube. The OpenRocket website itself, Rocketry Forum, all the places you would normally expect to find people talking about this sort of thing. So, yeah, lots of good info out there. I'm going to cover pretty much everything today, start to finish. I wouldn't call this just a basics video. There are some settings we won't cover. I may do follow-up videos in the future, or like I said, if there's something that you are trying to do that isn't covered here, just reach out. So let's go ahead and get started. The first thing you're going to want to do is go to your favorite browser and head to openrocket.info and download the client. So right on their homepage, you have a download button for the Windows client. This is the version that I'm going to be using. If you're running a different operating system, those download links are here. I'm not going to cover all of the step-by-step for installing it. It's pretty straightforward. Download the installer and run it. So let's go ahead and get into OpenRocket. So when you run it, it should look something like this. Before you dive into the actual design, the first thing you're going to want to do is go up to this Edit drop-down menu and go to Preferences. There's just a couple of things in here we want to make sure are set up correctly. There's a bunch of tabs in here where you can change some other settings. We don't really need to go through all those in detail. Launch settings are in here, but we're going to update those in the simulation section instead of configuring them here. So units is the main thing we want to update here. I like metric. I understand metric. I don't think in metric. So if you're like me, go ahead and hit default imperial, and it'll update all of these to inches, feet, degrees Fahrenheit, that sort of thing. If you want to stick with metric, going to default metric, of course, changes all those over to centimeters, millimeters, grams, things like that. I'm going to stick with imperial with the exception of one setting, and that is motor dimensions. So all of the motor case sizes, the kind of standardized commercial case sizes in amateur rocketry are defined in millimeters. So the rocket that we're going to build today, for example, is a 29 millimeter motor mount rocket. So I'm going to switch that one drop down back to millimeters right there for motor dimensions. Materials is the other one that you could update if you feel like you have a material you're going to be using that isn't already in the system. It's actually probably not super likely. They have a lot of stuff in here now. A lot more options have been added in the last few years. So scroll through this list and look at the different materials that are available. If you think you're going to be using something that isn't in here, you would just hit new and create a new material profile so that you can assign that material to components as you design them. The graphics tab is the last one here. This is another thing where we don't really need to mess with it. There's a couple of graphical components to OpenRocket. They're definitely not critical to the design or simulation stuff. Okay, so let's actually get started with the design. Your first window up here in the top left is your component tree. So it's always going to start with a rocket and a first stage called sustainer. For any single stage rocket, this is going to be what you're going to start with, and you won't need to change any of that. If you wanted to, anything in the component tree, you can double click on and edit. So let's say we want to change the name of the rocket today to tutorial rocket, and I can say that I'm the designer. If you have multiple people working on a design, these fields could be a lot more helpful for keeping track of what everyone is in there doing. And one other note that I'll make is the comments section is something that's going to show up in tooltips. in the component tree. So what we're building today is an Estes Doorknob kit. This is just a mid-power kit that I had on the shelf here to use as an example. So we'll say okay, and now as you can see when I hover over Tutorial Rocket, right there it says single stage Estes Doorknob. We're going to go to Sustainer and start adding components. So the Sustainer is what's, it's referring to this first stage in the construction. If we had a multi-stage rocket, they would still fall under the Tutorial Rocket sort of banner here. But we would click stage, and now you'd see we have a whole separate stage here. That comes into play when you're building a multi-stage rocket and have multiple motors and ignition events. We're not going to use that today, so I'm going to delete that. Anytime I'm clicked on something in the component tree and I add a component over here, it's going to add it below that item in the tree that I'm clicked on. So we'll select Sustainer, and we're going to start with the nose cone. We kind of work left to right in the view, or top to bottom on the rocket as we add components. So this screen you're going to get is a component configuration screen, and you're going to define everything about that component in terms of dimensions, material, weight. There's some other parameters you can change that are specific to that component type. So for example, we are using an ogive nose cone. This slider here, or this shape parameter value, is going to change it from, well, it describes it right here. It's going to change it from a true tangent ogive to secant ogive. As I slide this slider down to 0, it basically becomes a conical nose cone. And you can kind of see, if you watch this view down here, you can see what that's doing to the shape of the nose cone. This is a tangent ogive, so we're going to leave it at 1. And now we're going to switch over to a camera I have here on my workbench, so you can see the components that I'm working with. So first up is this nose cone, and we want to know how long it is. Nose cones are always tricky to get exactly right if you didn't fabricate them yourself. This one's going to be 9 inches. So we'll come back over here, and we will click in the length field and just type 9. Tab down to the next field, and now that nose cone in this view is 9 inches long. The base diameter is going to be the diameter across the base of the nose cone above the shoulder. So we'll take our calipers here, and we're getting 3.15. And I know the actual design of these 3-inch rockets, it's supposed to be 3.1. So I'm going to go ahead and put in 3.1 because I would trust the manufacturer on this more than my old analog calipers. Okay. Next is wall thickness. That's pretty tough to get for plastic molded nose cones like this. I'm going to guess that it's about 0.5. So we'll just go like that. It is not filled, so we will not check that box. And now over here we have material. So we're going to scroll down on material and select polystyrene, I think is closest to what this thing is actually made of. Lastly, component finish. This dropdown is going to affect the drag calculations, and it says that in the tooltip for this dropdown. I like to change this to unfinished. It seems to give me the most real-world results based on, I'm often spray painting a rocket, or my kids are putting stickers on it. So an unfinished value for surface roughness here is going to give me the most accurate simulation for max velocity and apogee. If you know the surface roughness of your components, props to you. It's a difficult thing to measure, but you could select whatever surface roughness you wanted here based on actual values if you have them. So we're going to go with unfinished across the board for all the components that we put in here today. One thing that I skipped that is probably turned on as a default for OpenRocket when you first download it is when you clicked on the button to add the nose cone, you probably got this screen. I'm sorry I skipped over that before. I unchecked this box down here in the lower left whenever I set up OpenRocket for the first time. This is a parts library. They've put in all of the values that you need to create components coming from commercial manufacturers. So this list is huge. And if you have a part number for the component you're using, you can go in here and select it. I still just kind of like to build mine from scratch to make sure that I'm using real world values. Like I said, with the nose cone, I knew the diameter, knew what it was supposed to be. There's other components in here where, kind of regardless of what it's supposed to be, I'm going to measure it and use the value that I actually get. Things like lengths of tubes can change a little bit. Certainly the mass of a lot of components can change from what's in here. But that's what this is. This is a component preset library. You can either just scroll through it, or certainly the best way to go would be to filter by text and search for whatever component you're looking for or part number that you have for the component that you're adding. But I don't turn this on as a default, so that wouldn't have been there. If you want to get to it again, it's in this configuration screen in the top right. It's this button that says Parts Library. Okay, so we have the nose cone down here, mostly modeled for the actual exposed part of the nose cone. The next thing we're going to do is the shoulder. So if we come back over here, this is the shoulder right here. So we need to know width, height, and again, the thickness, which we'll just do at 0.05 for this one as well. So the shoulder diameter is going to be 2.9. Yeah, 2.9. Actually, we'll just measure height while we're here. So that's going to be from here down to the base. And we're talking 2.85. They're almost both 2.9, but we'll put in what I got. So diameter is going to be 2.9. Oops, missed my decimal. And the length is 2.85. I think that's what I said. And a thickness of 0.05. So now, and it is end capped, so we don't have a bulkhead that we need to add for this. So now you can see that model down here. This is going to be the part that obviously slides into the top of our body tube. In a component configuration screen, we have a few more tabs here. Override is going to be on most of them. You can override the mass, center of gravity, and the drag coefficient. Again, great if you have actual values. These are really tricky to measure on certain things. Center of gravity on things that aren't symmetrical, and drag coefficient certainly would be a difficult one to consciously override. Mass, we're going to override almost every single time. I'll leave them for now, and then we'll see how accurate our model ends up being. This specific component is really close. I measured weight on all these components before I started, and the nose cone came out at 2.75 ounces. So 2.72 here is the default value, is pretty good. And it's basing that on the wall thickness, the overall size, of course, and the material. That's the main thing the material is providing on this first screen, is that material density. So that's the override tab. The appearance tab can be used to actually change the color of a component. You can even add decals if you want to. We're not going to play with that today. It does not affect the simulation results. But some people really like putting in real appearance of their rockets just so they can, I don't know, remember which one's which, or actually see if they're designing decals, like what fits, that sort of thing. The comment section, same thing. Anything you put in here is going to show up as a tooltip on your component tree. I'm going to leave it alone for now. So there's our nose cone. Next, we're going to add a body tube because we're working from the tip of the nose cone to the bottom. And now that we have a nose cone, some of these other buttons have popped up that we can add to the nose cone, but we're just going to use the very next one, body tube. So once you have a nose cone, adding a body tube component, it's going to automatically calculate the outer diameter and the inner diameter based on the dimensions, or sorry, I take it back. It's only going to automatically calculate the outer diameter. Inner diameter and wall thickness are related if I make this 0.1, it should, recalculate that inner diameter to 2.9. I'm going to actually measure that value and see what we get. Hopefully it comes out pretty close to what the simulation wants it to be, so that we don't get any body discontinuity errors, which is a thing we'll cover in the simulation portion. But the outer diameter is calculated based on the base diameter of the nose cone. The length we need to measure. So we will come back over here, and this is just the full length of my body tube here. I'm going to use my tape measure. 18 inches. Like I said, this is kind of a short, stubby rocket. It seemed like a good candidate for an example today in here. So we'll click on length, change that to 18 inches, and now we can see our nose cone attached to our body tube. So if I come back over here, that's what we're looking at. This is the bottom of our rocket. Slide that over. You can see the nose cone installed on top. Sorry, I can't pan out farther than that, but that is what we have going on here. Take some calipers really quick and measure the wall thickness of my tube and see how close we are. 0.05. So it should be exactly half of this. I guess this wouldn't be a terrible time to mention. If I have 0.1 in here and I want half of 0.1, I can actually just type that formula. Oops, I hit divided by 5 though, which was the wrong thing to put in there. So divide that by 2 and it gives me that 0.05. I realized that was some pretty simple math, but if it were more complicated than that, you could use that function as well. Okay. This one is cardboard. I think that's the body tube kind of default material, whereas the nose cone default material I think was balsa wood. So this one we can leave alone. And we have, we're going to want to change the finish again to unfinished. The motor tab on a body tube is so that you can declare that component a motor mount and mount a motor in the simulation in that component. This body tube is not a motor mount, so we're going to leave that unchecked. We will check this box for our motor tube, which is one of the next components we're going to add. The override tab on this one, we have the same three things: mass, center of gravity, and center of drag, drag coefficient. The mass on this one, it's saying is 3.39, and I measured this one at just 2.8. So I'm going to go ahead and override this one right now. So I'll just check that box, click in here, and put in 2.8. So if you have masses for your components that you've weighed before you start building or doing your simulation, go ahead and just put them in. If you have built the rocket already, what you'll be able to do is break the rocket down, real world, into whatever the smallest pieces are that you can break it down into, and override those weights at a higher level in the component tree. And I'll show you how we do that later on as well. And then we have appearance and comment again, and I'm just going to leave those alone. Okay. Some people at this point do fins next. I like to do the internals so that OpenRocket will automatically calculate fin tabs for me, and you'll see what that looks like when we get to the fin section. but we're going to start with the motor mount tube. So that component in here is called an inner tube. This is just a tube inside of the airframe or body tube somewhere with a much smaller diameter. You might be building a kit that has a coupler, which is a cardboard tube that slides into the body tube with like a mating outer diameter to the inner diameter of your body tube. So if you're building one of the Lock Precision kits, for example, you should have a coupler that's attached to this first section of body tube, and then that coupler will have a bulkhead in the end of it, and then in the assembly that coupler tube will attach to a whole second section of body tube that would go over to the right here. This kit doesn't have that. It's just a single body tube, no bulkheads or anything, no couplers. So I'm going to ignore those for now, but once you've done the rest of this, adding any of those would be really straightforward. So this inner tube is our motor tube, and like I said, it's going to be kind of any diameter that we want. So let's measure it. So this is my motor tube. This is for a 29, like I said, a 29 millimeter motor mount. It's kind of one of the key defining characteristics of a lot of rockets. It's something a lot of people will ask you about a rocket is what size motor mount is it, or what size motor does it fly on? And for this rocket, that's going to be an 8-inch long, 29 millimeter motor tube. So I need the length, but really that inner diameter is the most important part. So we'll come back over here. Our length is 8 inches. Our outer diameter is more than 29 millimeters. And we're in inches anyway. So we'll just call it 1.2. So we click into outer diameter 1.2. It's calculating the inner diameter based on the wall thickness right now, and we're going to fix that, of course. So we'll come back over here, and our inner diameter, I believe 29 millimeters is 1.14, 1.13, 1.14, somewhere in that range. Yeah, and 1.14 is what I'm measuring. I think it's actually closer to 1.13, and maybe I've marred that a little bit with my sharp calipers, but that's okay. So inner diameter we'll say is 1.14, and now it's calculating that wall thickness for me at 0.03. We just have the material drop down here. Being an inner component, this component is not going to affect aerodynamics at all, so you lose some of those other things that you might need to edit in here. A new one that we have is placement. So with a nose cone, you can think of it as sitting at the origin. Think of the tip of the nose as kind of the origin point, if you're familiar with CAD work. And then the body tube has to sit on the nose cone shoulder. It also doesn't really give you an opportunity to move that. But this component, it gives us this placement section here, and we can either manually edit this number, or we have a slider here, which is good just for me showing how this works. I can move it around, and right now it's set to bottom of the parent component. So the bottom of the motor mount tube relative to the bottom of the body tube. And I'm going to go ahead and leave it at 0. Going to go over to the motor tab, and this is our motor mount tube. So we're going to check that box, and we're going to change our motor overhang to 1/4 of an inch. This is just going to position the mass of the motor correctly, hanging out the back of the motor mount tube by a little bit. That 1/4 of an inch is an approximation, but the aft end or the nozzle end of your motor is going to have a thrust ring that does not slide all the way into your motor mount tube. And so that just gives that little bit of space there so that it's more accurately predicting the center of mass for the whole rocket once the motor is loaded in the simulation. Ignition, leaving this automatic is also fine for now. You can force it to ignite this motor in the simulation at certain points. This is especially important for stage rockets and clusters and air starts and all those things that would make a rocket complex. we're not doing any of that, so I'm just going to leave this on automatic, and it will ignite whatever motor we have in this motor mount at launch. We're not building a cluster rocket, so I can leave this tab alone. You can play with this in your own time if you want to see how this works. There's lots of options in here for different cluster configurations. Radial position for a motor mount, I'm not sure why you would want to do this, but you can move the whole motor mount tube off center if you would like to, and you can cant it inside the body tube. Not going to do any of that. So here on our override, you can see the drag coefficient on this is 0 because it's an internal component. The mass that I measured for our motor mount tube is 0.5. So this one came in a little under. I'm going to go ahead and override it to 0.5 ounce. And center of gravity is just, yeah, that's going to be an obvious halfway point because it is symmetrical top to bottom. Okay, appearance tab, comment tab, done. So now you can see this inner tube is underneath our body tube in the component tree. So this is where I was talking about if I wanted to, I could go to my body tube and I can double click it or I can hit edit. When I go to the override now, if I override the mass and I check this box for overriding all subcomponents, the component mass of that inner motor mount tube now does not apply to the overall weight of my model, and it does not factor its mass into the center of gravity calculation. So the more detailed mass information you can get component by component, the better. But if you've already built your rocket and you're just, in your hand holding your whole body tube and the whole motor mount assembly and the fins and everything, and you just have that all built up already, you can select that whole assembly over here in your component tree, override the mass for all subcomponents, and then weigh that entire subassembly and try and either measure practically or calculate somehow the actual center of gravity for that component. For now, I'm going to uncheck this because we do think we know the mass for our motor mount tube. We'll go back in here and make sure that that didn't mess that up. Yep, override mass to 0.5, so that's applying again. Okay, next is going to be centering rings. So these are these, in my case, they're plywood. They can be on a small rocket, they can be cardstock, they can be wood, they can be fiberglass, whatever. And if I am still selected on my inner tube and I click on centering ring, it's going to build that centering ring down here inside of my motor mount tube. I don't want that, so I'm going to hit cancel. I'm going to click on the body tube again and hit centering ring, and that's going to build the ring outside of my motor mount tube and inside my body tube, and it's going to calculate a lot of this information for me based on my body tube and motor mount tube geometry. So the outer diameter is 3. That's just based on the inner diameter of the body tube. The inner diameter is 1.2 based on the outer diameter of my motor mount tube. All I need to do is measure how thick it is. So we'll come over here. This is one of those centering rings. So this is that motor mount tube diameter. You can see that would just slide right on there. This is my body tube, and you can see that fits right in there. So all I'm going to do is take my calipers and check, and this was advertised on the kit as having 1/8" plywood centering rings, and indeed that comes out to, again, my calipers are measuring a little high, but 0.125, which is going to be 1/8 of an inch. So we'll come back over here. We'll go into thickness and 0.125. And then for material on these, as I said, these are birch plywood. And right now, this one's also set to bottom of the parent component, +0. And you can see it sitting down here. Another thing that I know about my rocket, if I come back over here, is that I have some fin tabs, and we'll talk about the fins in a little more detail in a second, but this is what the fins look like, and they're going to slide into these slots, and I want that centering ring to be up against this back fin tab right here, and that's going to mean that it's not at 0. So what I want to do is measure this distance here, which is going to be 1/2 inch. And then since I know my centering ring is 1/8 inch thick, I'm going to change this to bottom of the parent component, which again is going to the bottom of my 1/8 inch thick centering ring, and I want the top of my 1/8 inch thick centering ring to be 1/2 inch up. So I'm going to go in here and I'm going to say negative to move it forward. And then I'm going to say 0.375, or if I wanted to, again, I could say negative 0.5 minus my 0.125, and it would do that math for me. I don't know if I got my minuses in the right place in that, but you understand. And hit tab. And that's going to move this ring forward for me right here to where I want it. The mass on this one was 0.25, so it's got it pretty much right. We'll leave it in there, and that'll help account for some glue and stuff later on. So we'll say okay. I have 2 more centering rings on this motor mount tube. So again, I'm going to click on body tube and centering ring and build another one. Except that I don't actually want to build another one. I just built one. So of course I can cancel that and come up here and copy this and click on it again and hit paste. And now I have another one, and I can just double click on that and run this slider bar to move it around. And I pre-measured this just to save a little time, but I want this one to be 2.75 inches away from the very bottom of the airframe, because this one I want the bottom up against the edge of the fin tab that's going to go in here. My fin tab is 2.5 inches wide, so to get the bottom 2.5 inches away from the top of this one, because the top of this one, remember, we put 1/2 inch away from the bottom. So a little bit of math, we end up with this 2.75 for the position of that centering ring. Copying and pasting it just brings these values over. So the thickness is set, the inner and outer diameter, those were automatic, but still we know those are the same. And it also brought material over, and if I had overridden the mass, it would have brought that over as well. Okay, so we'll say okay. And you should also be able to use keyboard commands in here. So if I just click on centering ring, Control C, Control V, oh, it worked. Recently I was using OpenRocket and my keyboard commands weren't working, and I'm not sure why. OpenRocket is open source and they're iterating on it all the time, which is awesome. But you definitely find little bugs here and there, and I just chalked that up to a little bug, and I'm glad it's working again. So yeah, Control C, Control V, all those other keyboard commands, they all work in here. So now we have 3 centering rings. I'm going to click on this last one and go to my General tab and move it up here somewhere. The position of this one's less critical. And yeah, I can use this slider, or I can set an exact location. Let's say we want it about 1/2 inch from the top. So I'll go like that. That actually leaves that 0.375 exposed here, and the 0.5 is going to be from the bottom of that centering ring, but that's fine. We'll put that right there. Okay. So now I have my centering rings in there. It's time to do fins. So we're going to click on body tube again, and let's do freeform. Trapezoidal and elliptical, of course, come with some predefined features so that you don't have to do all the tinkering that you do with a freeform fin. But I like freeform fins. So go in here. The first thing I'm going to change is this rocket has 4 fins, not 3. Again, a lot of the kit rockets we use with PSAS are going to have 3 fins, so you'd be able to just leave that alone. My rocket today has 4 fins, so I'm going to adjust that there. I do not want to cant the fins. These are made of the same ply that my centering rings are made of, so I'm going to change thickness to 0.125. And the cross section is it's the profile of the whole fin. I'll go over here. If you looked at the fin on this angle here, rounded means your leading edge is going to be, it's going to be rounded because you're going to sand it or file it or whatever. and the trailing edge as well. So basically all of these squared off surfaces are going to be round profiles instead. Right now, my default value in there is square, which is what this currently is. It's hard to see in the camera there, but you can tell it's just a laser cut plywood fin. The last thing I have in this dropdown is airfoil. So that would be where if you used some kind of fixture to put straight, bevels on the leading and trailing edges of your fin, you might use airfoil here. These three options are going to change the simulation values a little bit. I've not done a ton of experimentation to see how much they change it, and I imagine they have the greatest effect once you're approaching Mach or actually going supersonic. In my case, most of the time I change this to rounded. That is often what I actually do with my rockets, is sand them enough to get those laser marks off there and round the leading and trailing edges a bit. Okay, we have the placement sliders again. We're not going to use that for now, but we'll probably have to come back and change it as we define the shape of the fin. We're going to change material down to birch plywood again. This set for all button that I've been ignoring, by the way, that's set for all components of the entire rocket. You do not need to click that button right here to set all of the fins. It's not going to think we have different material fins. It's going to use birch for all of them. This would change my body tube to plywood and my nose cone to plywood, and I don't want to do that. Sorry, this is all for finish. Completely forget everything I just said. Unfinished finish is fine, and actually I could do set for all on that. Let's go see, and let's go make sure really quick. I'll come back to this. Let's go make sure I didn't make my nose cone out of plywood. Nope, it's still polystyrene, so that's good. Okay, little detour there. So back to our fins. Plywood, unfinished, that all looks good. Fillets, yeah, we can add some little fillets. Let's say our fillets are going to be fiberglass. I'll probably just use a little bit of 2-part epoxy to do my fillets here. They'll be little fillets, I'll say a 1/2 inch radius. It's pretty easy to use something like a piece of PVC pipe or a popsicle stick to make a little 1/2 inch-ish radius fillet. So we'll do that. That'll add some mass for us. So these are going to come in heavier than what I've measured for them, and that's okay. We'll just leave it, and hopefully it turns out pretty close. Okay, shape. So fin shape in here, you get this big graph paper looking visual, and you have nodes for every change in the geometry of the fin. You can add these, you can delete these, and you can grab them and move them around. One thing that's not 100% intuitive in this screen is I'm moving this node, but the one that doesn't move in the visual is the root trailing edge node right here. But you can see how that adjusts, and you can see how that's reflected in the model back here. And what I'm going to do is come back over here to my fin. I'm going to measure a few things. So the tip of my fin is going to be 4.5 inches along the root. The tip of my fin is going to be 1.25. And we're going to have to do some math, but that's okay. And the span of my fin is going to be 3.25. And we'll come back and do the fin tab in just a minute. So if we come over here, I don't know why, but for some reason I like to use, instead of using this editor view here, what I will often do is use this little table right here. And this, as you click on these, you'll see it highlight which node it's talking about. So even though this is the one that it doesn't move in this view, this one down here in the corner is our 0, 0 point. Not sure why, that's just how it likes to do it. So what we're gonna do is change this to that 4.5. that's going to make, if you look down here, it's maybe a little easier to see. It's going to make this root edge of my fin 4.5 inches long. You can also see now that it has dropped the back of my fin off the bottom of the rocket. When I adjusted this value up here, it left this node where it was. So now I'll come back over here to the general tab and change this back to a 0. And it moves that fin back up to where it's supposed to be. So now we'll go back to shape and put in these other values. So my trailing edge is horizontal. So my X value is just going to be another 4.5 because this corner up here is 4.5 inches aft of my, this front corner of my leading edge here. And then let's see if we can all remember the span of my fin. I'm pretty sure it was 3 point, nope, I'm going to cheat and measure it in the background again. 3.25. That's totally what I was going to say. Okay, so now we have that out there, and that looks totally wrong, and that's because we haven't done this one yet. So we'll change that to 3.25 because the span is the same. And then the last thing we needed to figure out was how far this X value was from our leading root corner here. And I think what I measured was from here to here was 1.25, which means this is just going to be 1.25 less than 4.5. Is that right? Let's see. 3.25. Wow, I really missed on my keyboard there. Yep, there we go. So we put 3.25 in there. And now when you look at this fin shape here, it should match that fin shape there. So we'll come back over here and go to the fin tabs. Now, as I said, this is this part of the fin down here. It slides into the slot in the airframe and kind of locks between those two bottom centering rings. I could measure everything I need for that. Also ignore this little notch here. That's kind of an extra. I have another centering ring that has mating notches in it, which would change how this whole thing is laid out a little bit, but we're going to pretend that that's not actually there. I just wanted you to know why I had a big notch taken out of it. Anyway, the values for the length and depth of this, I can put all of that into OpenRocket here, including the position. So that's kind of where the tab is protruding from the bottom of the rocket. But we have this great button down here that just says calculate automatically. When I hit that button, hopefully you saw those appear right down here. It's now created those tabs for me. It's going to use the same thickness as the fin, of course, and then it's going to locate the position of the tab between those two centering rings. Yeah, that's pretty much all you need to do for those. So that's why it's really important to have your motor mount tube and your centering rings in there to begin with. If you don't have those, if you don't have a motor mount tube, the tabs will go all the way to the middle of the rocket. If you don't have centering rings, the tab will be the full length of the fin. Okay, override, we'll leave mass alone. One fin on its own, I measured at 0.55. And this mass, by the way, is for all 4 fins. So if I add that up, I'd be at 2.2. So it looks like I'm adding about 1.2 ounces for my fillets that I added at the start. Hopefully that's about right. We can kind of double check all that once we have the whole assembly actually built up. So I think that's pretty much it for fins. We'll say okay. All right, we're starting to look like a rocket. Let's see. Next, we should add some other mass components that we might have on this rocket. So we'll click on inner tube and scroll down here. And I'm going to add a mass component. And I'm going to call it motor retainer. So the motor retainer is, I'll come over here really quick. This is a motor retainer. It's a thread-on motor retainer. So you have two pieces here. This one glues onto the motor mount tube, and then once your motor is installed through that and into the tube, you use this to cap it off. So this just slides on there like that. And then when this is installed in the rocket, it's really easy to just throw a motor in there and close it up. And then your motor doesn't fall out the back of your rocket when you fly your rocket. So what we're going to do is call this mass component motor retainer. And we're going to put it on the bottom. And now you can see it moving this little thing around right here. I'm going to make it just 1/2 inch tall. And it weighs about 1/2 ounce. So we'll put that back there. And we'll make it a little wider. We can use the slider here. Great, so there's our motor retainer. We don't need to do anything in the other tabs here. And let's add another piece of hardware. Let's go to our forward centering ring and add, it's not gonna let me add a mass component to the centering ring. So let's go to inner tube and add another mass component. And this little component is gonna be the eye bolt that we would attach our harness to. So we can go like this. And here's an example of where you might adjust this radial position. This eye bolt's going to be installed in our top centering ring. We're going to put a hole right about there in the middle of that centering ring to put an eye bolt in. So we'll just approximate that. It's going to be 1 inch away from the center. So we'll say radial distance is 1 inch. And then, if I come back over here, I put 1 inch under radial distance right here. And then what you can see it did in the model is moved it up here. So it's not sitting right on the center line of the whole rocket anymore. That's not going to affect a whole lot. It is going to move some of that mass off the center line, which will factor into the simulation values a little bit. But for something this light, not a lot. Oh, I guess I didn't put in a mass at all, but we'll say it weighs 1/4 ounce. I'm not actually sure on that. But we can put that in there just so we have a complete list of what's in the rocket. Right, we'll just call it eye bolt. Okay. All right, let's add some recovery gear. So we'll go to our body tube again, and we'll start with our shock cord or our harness. I'm going to change the name to harness. Shock cord usually kind of implies the elastic shock cords that come with little model rockets. When you're building bigger rockets, you're going to use something more rigid, and we're going to call it a harness. It's going to be made of nylon or Kevlar, or maybe a combination of materials. Anyway, we're going to call it a harness. My harness I have for this rocket, I want to say is 6 feet of Kevlar. Yeah, we'll just go with that. So 72 inches, and we'll change it from this little elastic cord. Kevlar thread. I think it's closer to 12 strands. So we'll say it's 3/8 inch 12 strand Kevlar. Okay, so it's created that right here. And we're going to just use these sliders again. It's a little easier with these squishier objects to just use the sliders. We'll say it's going to take up about that much space vertically, that much space in diameter. And then we're going to move it down. Even if we packed it right here when we close the rocket up, when the rocket takes off, it's going to slide to the back. So we'll put it right here sitting on top of the motor tube. That looks good. Okay. Radial position, don't need to adjust. Override mass, no, we'll leave that alone for now. Actually, 3.8, that's way too high. We are going to override the mass. Let's call it 1 ounce of Kevlar. Okay. Same thing with the parachute. Click on body tube, click on parachute. This kit comes with an 18-inch diameter parachute, so that's going to be your first field there. It is made of nylon. Drag coefficient at 0.8 seems pretty reasonable. They can get a lot higher, but if you're going to adjust the drag coefficient, make sure you've gone to your parachute manufacturer website and seen what they advertise as the known drag coefficient for the chute that you're using. Okay, shroud lines. This one has 8 shroud lines, and they are, this was a lot of measuring, so I did it beforehand. They are 20 inches long, and my shroud lines are, we'll call it heavy duty thread. I'm not sure exactly, but I know that they're not going to weigh much, so we'll put it in as heavy duty thread. Okay, same thing. This created a component that I can see down here in my model, and I'm going to make that a little longer and a little wider and drag it down here somewhere. Packing harnesses and chutes isn't a super exact science in a model like this. If you are using deployment bags or have very specific location control for your recovery gear, obviously take the time to take more precise measurements for these because they're definitely going to contribute to your center of mass as it's calculated in the model here. Okay, I think that's good for parachute. The last thing that we can do here that I know is going to be on this rocket are some rail guides. This is a relatively new feature in OpenRocket, but it's great. Go back up to our body tube and come over to rail button. And these values, I believe, are all defaults for a 1010 rail button, which is going to be what you're going to use on a lot of rockets, everything from mid-power up to, you know, level 2 size rockets, stuff flying on J's and K's and even L's. So we're going to leave all of this alone. I can just see, looking at the visual of it down here where I added it, it looks about right. All I'm going to do is I'm going to use 2, and I'm going to spread them out a bit. Actually, the best thing to do would be to have one going into each of my center rings, the one into each, the top and bottom. So I'll do that. We'll see how that works out separation wise. I'm not sure exactly yet. And then we'll slide these down. Yeah, that's just about it. 1.7, 1.3. So we'll make it 1.5 right here for location. We'll make it 1.4 for location. And that puts them just about in those center rings. So that's where those are going to screw in. And they are made of Delrin, and they are, we'll say, actually Delrin's, the way these are manufactured, they're pretty shiny. We'll say smooth paint on these. So now that those are there, those will also factor into our aerodynamic, our simulation values. And we'll leave the weight too. I bet that's pretty good on those. So we'll say okay. One thing we can do once we've added external components is in this lower view here, we have a drop down for the view. So there's top view and side view, which look pretty much the same as you can see, but I can also go to 3-dimensional renderings. So this one's, it's called 3D figure. Some people might like looking at this view. It's more, I don't know, call it an X-ray view of the rocket. And you can see now, looking back here, that this isn't a straight on view. And in fact, I can click on it and spin it. So I can spin it this way and I can spin it this way. You can also do this with unfinished and see kind of what it thinks your components might look like unpainted, and you get that X-ray view still. Or finished, and this is where it's going to cover up the inside and you can actually see what your rocket looks like built. And if I had changed any of those appearance things, those would be reflected here. So if I had painted the fins a certain color or put a decal on the body tube, that's where these would show up. And in the bottom, I can kind of see that I've put on yeah, you can see my motor retainer down there. But what I notice is that my rail buttons are in line with my fin, which I do not want. So we'll come back over to rail button and we will rotate these back by 45 degrees. So I'm going to put in 135. This field right here actually it's going to limit you to between 0 and 180 degrees. So I can't put in whatever that would be, 225. I need to put in 135. So I say okay, and that spins my rail buttons around so that they're centered in between two of those fins, which is definitely where they will be when we fly. Okay. I think that kind of covers the design portion. There's some other things in this bottom pane I didn't really touch on yet. In the top left here, you have some overall values for your rocket. Overall length, in this case, we're at 27 inches. Diameter is 3.1, and the mass with no motors is 12.5 ounces. In the bottom left, I can see simulation data, basic, just apogee, max velocity, and max acceleration, if I have a motor configured, which I do not yet, so there's nothing there. Once I have motor configurations set up, they will be in this dropdown, and again, I don't have any yet, so there's nothing there. And in the top right, I have basic stability values. So right now my stability is at 0.787. I want it to be 1. It's not, so we're going to have to do something about that. And it gives me dimensional values for my center of gravity and center of pressure. So center of gravity is this little blue graphic right here, and it's telling me that it's about 18.5 inches away from the tip of the nose cone. And my center of pressure is just shy of 21 inches away from the tip of the nose cone. And that's where it's getting that stability value. That is the ratio of the distance between these two locations, the ratio of that distance to the body tube diameter. So at about 18.5 and about 21, you're talking about 2.5 to 3, right? So you have about 2.5 inches from here to here and 3 inches here. So 2.5 divided by 3, you get 0.787, using whatever these actual values are. We want it to be 1. We want the center of gravity to be forward, up here somewhere, forward of our simulated center of pressure by at least 1 body tube diameter. And that's with a motor in it. And we have not loaded a motor yet, and loading a motor is going to pull the center of gravity back even farther. So let's load a motor. Let's see how bad our stability gets. And then I think what we're going to end up doing is adding another mass component up here that is just ballast. But let's go to the next window, motors and configuration. So you're always looking at your rocket, but you have this pane up here that's going to change. And on motor mounts, on this menu over here on the left, we have our inner tube, and this will update if you change names. So if I go back over here, go to my inner tube and call it my MMT, is a initialism you'll see used for it a lot. It's just motor mount tube. It's very creative. Now when I come over here, this will say MMT. So I'll check MMT if it's not already checked and hit new configuration. So this is where I pick the motor that my rocket's going to fly on, or motors if I want, if I have a cluster, and I can create new configurations for all of the different motors that I want to see how it will fly on. So to select motors, you start over here, you pick the brand of motor that you're going to fly. We'll go with Aerotech, very popular brand. This is a pretty small, lightweight, mid-power model, so I'm not going to fly it on high-power motors. I wouldn't want to fly this on anything bigger than a G. I could definitely fly it on something as small as an E. Could probably fly it on something as small as a D, but we'll sort E to G from Aerotech. And then I don't want to have to use an adapter to use smaller motors. I just want to look at 29. And this is one of those sliders that in the settings where I change to motor dimensions being in millimeters, I see that right here. If I had not changed to that, my motor diameter options would be 1.1, 1.5, 2.05, whatever they are. These would all be in inches, which is just kind of annoying because that's not the nomenclature anyone uses for motors. So we're at 29 millimeter. I like this F67. I've seen these fly. I know they're easy to get a hold of. Our vendor on site always has them. So I'm going to pick the F67. And then I'll just leave the delay. So these ejection charge delays are going to be the options you can find from the manufacturer. All of this motor data is populated from thrustcurve.org, which is a big online motor database for amateur rocketry. And so these values you're not going to be able to change. This is not a slider or something where you can just type in a number. In bigger motors, it's not going to matter because they're going to be plugged and you're going to be using electronic deployment. For smaller, model and hobby mid-power kind of motors, you just have to pick from whatever your options are. And if none of the options for a certain motor are good for your rocket, don't use that motor. So we'll leave it on 4 just to see what happens. And that's pretty much it. You have another, one more slider down here for motor length limits. If you use an engine block, you would need to set this. But with motors that have thrust rings in the back, you don't need an engine block in the front. So there's really no reason to put them in and limit yourself when it comes to what motors you can use. So we'll leave this alone. Okay. I guess just while we're here, if you click show details over here, you can see the thrust curve data for this motor. You can see it burns for 0.8, 0.9 seconds or whatever here on the graph. You can also see all of that up here. Burn time is 0.846 seconds. This is all the data from the motor certification process. So there's definitely some variability here in the real world, but this will give you a really good idea of how this one's going to perform. Okay, so F67W with a 4-second delay. So now you can see that here we have an F67W-4, and now we can see it loaded in the rocket down here, and you can see that it's hanging out by that 1/4 of an inch that I put in. And we can also see now that my stability is all the way down to 0.36, which is terrible. So let's just go ahead and add that other mass component. Let's put it, we're going to put it at the base of the nose cone shoulder. That's realistic. It'd be great if we could get it all the way into the tip of the nose of the rocket. That's not always feasible. So just for sake of ease, we're going to put it right here. So I'm going to put it in the body tube. I think if I put it in the nose cone, it's not going to let me get it any lower than like the base of the base diameter. So we'll go to body tube. We'll add a mass component. We'll call it ballast. Hopefully ballast is spelled with 2 L's. And let's put 4 ounces up there of just something. Doesn't matter what. We'll leave the size. It'll probably be a little, a lead weight or something. And then we'll move it to right there. So if I do that, now we can see my stability is 0.856. Still not 1, which is a bummer. I think this rocket would probably fly and be aerodynamically stable, even though my stability margin on the pad isn't at 1. And that is because this would be considered a short, stubby rocket. I don't know the technical term, but stubby rockets are rockets where your overall length to diameter ratio is, I can't remember the benchmark, maybe less than 6:1 or something. And in those cases, rocket stability is also affected by the base drag of the diameter of the body tube. And so you get some wiggle room there. It would be another video to show how you can model that base drag in OpenRocket. You add a component off the end here that's sort of a massless conical shape, and it adds that base drag factor into the stability calculation. So even though this is really your caliber of stability, whether that is stable or not is figured out using that trick. So I'm not going to do that right now. And even though the caliber is less than 1, I think it's still going to give me good simulation data. So I'm just going to leave this ballast at 4 ounces. That should be just fine. Okay, so our design is totally done now. Our motor is configured, and we're going to do our simulation. So It's already created a simulation record for me as soon as I added the motor configuration. So that's already here. If I wasn't sure if it had run, basically for any configuration in the simulation window, you can click on it, single click on it, and hit run simulation. And when you run these simulations, you will get slightly different values sometimes. So if you watch flight time, for example, there it went down to 4.12. Time to apogee changed a little bit. That's all changing based on standard deviation of wind in the simulation settings and maybe some other stuff. There's definitely things under the hood in OpenRocket that I don't know everything about. But yeah, this is not always going to be exactly the same. And it's giving me a warning here. Let's see what that warning is. Recovery device deployment at high speed, 94.9 feet per second. So if I read through all my stats here to try and figure out what that means, let's see, 100 feet per second off the rod. That's great. If this is too low, I'll get another warning over here. Apogee at 973 feet. That's pretty good. Seems just fine. Velocity at deployment, 95 feet per second. Yeah, that's super high. So what that means is the rocket is still going up really fast or sideways in the wind or something when the parachute ejects and tries to come out. And if we do that when we're going 95 feet per second, we're going to rip the chute apart, or the parachute and the harness are going to rip the body tube apart. One or the other, or both. Bad stuff. We don't want that. So let's figure out how to fix that. Our optimum delay is 6.82 seconds. So this is really important. If you remember back in the motor configuration tab, we left the delay on 4 seconds. So if 4 seconds into the flight, the parachute comes out, this optimum delay is telling me that ideally we'll be at apogee 6 seconds into the flight. So my delay is 6 seconds plus, well, it's probably factoring in some lateral velocity time too. So don't really think about time to apogee. Look at this optimum delay. This is really what you want to focus on. So with 6.82 or 6, either way, we definitely want to come back here and click on select motor again to edit this motor configuration and change it to 6 and just hit OK. So now we're using the same motor. It's just we bought and are flying the version of it that has a 6-second delay. So now it's an F67W-6. We'll go back to flight simulation. Oh, great. Now we have a green check mark. No warnings. Our new velocity at deployment is down to 27.3 feet per second, and it's happy. So it's updated this for me as soon as I changed that motor configuration. If I wanted to, I could add another configuration here, and we could fly it on a faster motor. We could fly it on a G40. And we know that's a bigger motor, so we're going to want at least 6 seconds of delay. Let's make it the full 10 seconds and go back over here. So now we have that second configuration, and now we have a second simulation. And this one's saying deployment at high speed, 80 feet per second. So now I've gone over, so it says the optimum delay is actually just 7, so I guessed wrong. It shouldn't be 10 seconds. That means that rocket's going to go up, it's going to arc over at the top, and it's going to be starting to come back in ballistic when that parachute pops out 10 seconds after motor burnout, and we don't want that. So we'll go back to here. We will edit this and make it a 7-second delay, and that's probably going to be as close as we can get. Come back to simulations. We have that same green check mark, and our velocity at deployment is 17. And that's actually better, to be honest. That's the slowest, the slower of the two that we have so far. So really, if I took this rocket out to the field, I would say that G40 is my greatest chance of success. Being a 40 Newton average thrust motor, my velocity off the rod is a little lower, but 84.5 is still plenty. I'm going a lot higher. I'm going to 1,700 feet now, so hopefully I have a friend to help me keep eyes on it. Otherwise, this flight profile looks fine. I'm still not going anywhere near Mach. This is definitely something this rocket should be able to handle. Ground hit velocity is the last value you have on here. We can change this by either making the rocket lighter or making the parachute bigger. I should say slower so that we run less risk of damaging something when it hits the ground. For a small rocket like this, below 30 is probably fine. On bigger models, I like to aim for 20 feet per second or less. But I mean, these are kind of the motors that this rocket's designed for, and the parachute that comes with the kit is designed with that in mind. I think it would probably be just fine. So now that I have these two motor configurations, under flight simulation, I can run a new simulation, pick which configuration I want, and change my launch conditions. So simulation 3, I can change the name to high wind. And these are all of my default settings that I had for my launch site. I guessed an average wind speed of 8 miles an hour just based on kind of the conditions that I like to fly in and the conditions we normally have at our launch site in Central Oregon. It definitely can get windier than this though, and we're still allowed to fly. So let's say 15 miles an hour. We'll leave the rest of it alone. 270 degrees means the wind is out of the west, and it kind of explains that in some tooltips here. These are the rough values for our launch site in Central Oregon. We're way up at 4,500 feet above mean sea level. These are our approximate coordinates, and we're flying off of 10-foot rods, and we angle them 2 to 3 degrees. And if it's windy, we might do more, let's say 4 degrees. And 0 degrees means they're angled to the north, which is true because our flight line is south of all of our launch pads. So we angle them away from all the people. Okay, so this is now our high wind simulation. And we'll say okay. And then we'll run it. And a lot of these values are going to be similar to what they were for this one up here. We're going to go a little lower, probably because our rocket is going to turn into the wind a little bit more. Our delay is going to be about the same. Certainly when we're just using these commercial motors, we're just going to choose that same 6-second delay. But you could see how you might use that to create different different simulations for one configuration and see how some of those values might change based on your launch conditions. This is also really helpful if you were going to fly at a totally different launch site. Not a lot of launch sites are that high up above sea level. And so if you were going to fly, say, at one of the Gorge rocketry sites or out in Yamhill, some of those other launch sites that we've talked about, you would want to change that. The other thing that you can do with any of these is plot or export. And so we have a button here at the top for that, or when you're in a simulation edit window, you have a button for it down here as well, simulate and plot. So when we go to this screen, we can choose the values that we want to see in our graph. There's some other things you can configure here, of course, which events you want tabbed on the graph, and the units that everything is reported in. We can add more if we want to. It'll add them just with the default total velocity because that's what's at the top. But there are a whole bunch of things that you can add if you want to look at roll, if you want to look at how CP moves, your center of pressure moves as you go through Mach transition, stuff like that. Tons of options in here. So we'll close that one. And then you can plot these and get a big on-screen graph. Super cool to look at and visualize how your launch is going to go. This green one in particular is lateral distance. And so this is kind of during the flight, and then it thinks it's going to drift about 370 feet away from where we launched it in some direction. I'm not sure which one of these. Let's see. Lateral directions. This purple line. It thinks it's going to go mostly north, I think. If I'm reading that correctly. That's not something I use as often, but yeah, you get the point. The other thing that you can do here is you can export an image of this graph to include in reports, or instead of plotting it on the screen back here, you can actually go to the export data tab and send all of this to a CSV file to look at or analyze in Excel or however you'd like. Okay, but we're not going to do that right now. We'll close that. I think that's pretty much it. So we covered rocket design. These are all kind of your basic components. Motors and configuration, select motors in here, and a lot of the default values in here are going to be fine. Oh, there is another tab here for recovery next to motors. It's going to default to ejection charge of this motor, which is again why default values are fine. You would need to get in here and change things if you have multiple recovery devices and or if you're using electronic deployment. So instead of the ejection charge in the motor, you would hit select deployment and you'd edit some things here. And then, yeah, we talked about flight simulations, different simulations versus different configurations. I think that's pretty much it. Thank you. I hope this was helpful. And again, if you have questions, find me. And yeah, that's it. Go build rockets.